Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find the green shaded triangle area? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. The green target is the right triangle ABC, not the quarter circle sector around it. Its right angle is at B, and the two legs segment BA and segment BC are equal radii. We need the area of triangle ABC. Near the arc sits a small construction along a vertical line DEF. The short segment DE is 2. The slanted segment CE is 3√2, and the segment DF meets the horizontal side BC at a right angle. These three clues are exactly what will pin down the radius. Because angle ABC is 90 degrees and segment BA equals segment BC equals R, the green triangle has area 1/2 R squared. So we only need to recover the radius from the small construction. Corner B is a right angle, and the two straight sides, segment BA and segment BC, are both radii of the quarter circle, so they are equal. That makes triangle ABC an isosceles right triangle, which fixes its other two angles. In an isosceles right triangle, the two base angles are equal and share the remaining 90 degrees, so each is 45 degrees. That means the chord AC runs at a clean 45-degree tilt. Point E sits on the chord AC, so the slanted segment CE lies right along that same 45-degree line. This is the fact that turns the little triangle into a special one. Now focus on the small green triangle, CEF. Its corner at F is a right angle, because segment DF is perpendicular to the side BC. Its slanted side CE of length 3√2 is the hypotenuse. Aha! The hypotenuse segment CE follows the 45-degree chord, while F is the right angle foot. So segment CE makes CEEF a 45. 45, 90 triangle. And its equal legs can be read from the given hypotenuse without touching the final area. In any 45, 45, 90 triangle, the two legs are equal, and each leg is the hypotenuse divided by √2. We will apply that rule to get the two legs segment CF and segment EF. Divide the hypotenuse 3√2 by √2, and the √2's cancel to leave 3. So both legs, segment CF and segment EF, are exactly 3. We will use segment EF to build a vertical length and segment CF to build a horizontal one. Because segment DF is perpendicular to side BC, the points D, E, and F are collinear, with E between D and F. Their lengths therefore add directly along the same line. Along that vertical line, segment DE is the given 2, and segment EF is the 3 we found. Add them, and the full vertical segment DF is 2 plus 3, which is 5. That is the first leg of the big triangle. The full horizontal side runs from B rightward to C with length R. The foot F sits 3 to the left of C, since segment CF is 3, so the left-hand piece segment BF is R minus 3. That is the second leg, and it still carries the unknown R. Now draw the segment from the center B out to the point D. Because D lies on the arc, this segment BD is a radius, so its length is R. This new line is the hypotenuse that ties everything together. Aha! Segment BD is the radius that closes triangle BFD. The same unknown R appears as the hypotenuse segment BD, while the base segment BF is R minus 3 and the other leg is 5. One right triangle now contains the whole radius equation. The Pythagorean theorem says the two legs squared add up to the hypotenuse squared. So r minus 3 squared plus 5 squared equals r squared. This single equation will give us r. First, expand r minus 3 squared. It becomes r squared minus 6r plus 9. Keeping this fully written out is what lets the r squared term cancel in a moment. Also, 5 squared is 25. Put the pieces on the left, so r squared minus 6r plus 9 plus 25 equals r squared on the right. Now watch the r squared terms. R squared appears on both sides, so it cancels cleanly and the equation becomes linear. The constants 9 and 25 make 34, and moving the 6r over leaves 34 equals 6r. Divide both sides by 6 to isolate r. 34 over 6 reduces, dividing top and bottom by 2 to 17/3. That is the radius of the quarter circle. Return to the actual target, the green right triangle ABC. Its perpendicular legs are both the radius 17/3, so its area is 1/2 r squared. Square the radius first. 17 squared is 289, and 3 squared is 9, so r squared is 289 over 9. Multiply the radius squared. 289 ninths by 1/2. The green triangle area is 289 18ths square units. As a check, r minus 3 is 8/3. 8/3 squared is 64 ninths plus 25, which is 225 ninths, totals 289 ninths, exactly r squared. The radius holds. So the area of the green triangle ABC is 289 over 18 square units. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.